Here comes a method for computing areas under curves. We're going to come at it from sort of a strange way here. I have this function, big F of x. Big F. For the time being, just ignore this function down here. What we're going to do is we're going to start off kind of, it's going to be like, where is this whole thing going? We're going to examine the changes in big F from x equals, so pretend I have an axis down here, right, and that this x-axis pertains to both of these functions. So this is x is a and x is b here, and we're going to examine how big F changes from a to b. If we were to compute the total change, all we would need do would be to do f of b minus f of a, and that would be the end of it, right? Because it would just be, it would just give you whatever this the difference in heights was, and that would be that. But we're going to do it from a slightly different angle. We're going to cut this thing up into, I have 3 different subintervals here. I could have done more, but I think that 3 is enough to really get my point across here. So what I'm going to do is I'm going to write the total change in F as the sum of these individual changes, right? How F changes from here to here, plus the change in F from here to here, plus the change in F from here to here. So let me get out my pen here, and I'll make let me make these triangles here. The first one, the first change in F is this. I'll call that, this guy here is delta big F1. Right? It's the first change according to how I have it cut up. And then since we're starting here and we're going over and down, this value here, I could draw it in red because it's down, but I want to draw it in green. This is delta F2. Alright, change in F2, and then the third one, if we come here, we go straight across and then go up. This is delta F3. Now, if we wanted to know the total change in F from this point to this point, all we would need to do would be to add delta F1, delta F2, and delta F3. And what they're going to do is they're going to add, and remember that this gets counted as a negative quantity because the point on the right is lower, right? These are, so maybe I should have drawn that in red because it's a down. These ones, these are going to add up to the total change. So say that in total the function goes up to, say, down 6 and up 2 again. That would be a total change in minus 2, right? And we wouldn't need to go through all this. We would just do it at the end point and say, oh, this one happens to be 2 less. But if you go up 2, that's a change in 2. Down 6, so that's a total change in minus 4. And then up the extra 2 again, that's a total change in minus 2 from here to here. So one more thing about this, I'll say that the total change in F, or rather F of B minus F of A, is equal to the sum of the delta FKs from K equals 1 to however many of these things I have, right? I only have 3 of them. But I could use as many as I wanted. I could use millions and millions and millions. But this is what we need to understand, right? This, the total change in F, equals the sums of the individual changes. Now, we use the mean value theorem. Because what I have graphed here, if I go wide a little bit, what I have graphed here is the derivative of this function here. So this function is big F prime. Big F prime of x. Now I don't really use big F prime. I'm just going to use just a little f for this. All right, and you'll see why in a second. But pictured here is the derivative of this function here. It's all drawn out nice, right? See, it's 0 where this has a dip, 0 where it's got a bump, 0 where it's got a dip. So this indeed is the derivative. What we're going to do is we're going to use the mean value theorem like we did in the last video to rewrite these changes in F. We're going to replace them with an expression involving the derivative. Now if you remember, what we did was we said that this change in F, this green line here, can be written as the product of the change in x, I'll write it in blue here. All right, the change in x multiplied by the appropriate slope in here. Now the slope that was appropriate was the slope that gave you a parallel tangent. So in this case, if here's a, can we see that? Yeah. In this case, okay, the magic value of x1 star that's going to be nice. It looks like it'll occur right about here, right, where the slope of the tangent is parallel. So if I kind of draw this down here, I'm going to use this, make a little dotted line here, and on the derivative, which I now actually have shown here, on the derivative, x1 star is this value of x here. It's this value, and f of x1 star is this height. So what we're saying is delta f1 can be rewritten as this length here, this blue line, multiplied by this height here, and we could interpret that as the area of such a rectangle here. So what we're saying is the area of this rectangle, the base times height, is equal to the length of this green line here. All right, let me just run over that one more time. All right, by the mean value theorem, there's got to be some value of x inside here where the tangent, where the value of the derivative is equal to the slope of this line. So in this particular case, that happens to be here. If you look at the geometry, that's where the tangent is parallel, and we're going to replace delta f1 with delta x1, which is this length here, multiplied by f prime of x1 star. Let me write that down. That'll be x1 star is here. So this height, and we can interpret that base times height as the area of this rectangle. And then what we're going to do is, we're going to do, let me zoom in, the same thing with the other two. Okay, for this second subintegral here, I got to zoom in close here. All right, we're looking at, see our triangle here, it goes from here and down. All right, we want to know, to write this negative change is going to be this delta x, this length in x, multiplied by big F prime of some number inside here. And we can see that, bump it up here. So if I draw my secant line to the function, it looks like it occurs right about here. I know it's a little bit sloppy, but it looks like the tangent is parallel right about there. And if I follow that down, clearly it's going to be a negative value. But if I follow that down, this number here, right there, is my x2 star. Right, that's the magic number. So f of x2, I'm sorry, f prime, or big F prime, right, big F prime of x2 star gives me this negative number. And I get a second triangle out of it. All right, delta x2 is this, and the height is this. So that rectangle is like so. So the area of this rectangle is equal to this the length of this red line here, the original change in big F. And then I'm going to do this one more time. If we can see it all right there, that would be good. Okay. For this last one here, the change in F is this green line again. So we want to know where the tangent line is going to be parallel to the secant. For this case, it looks like it's right about here. Guaranteed to exist by the mean value theorem. And if I follow that down, I get right here. That is x3 star. That's the value of x that's satisfied by the mean value theorem. And so I will do it again. So big F prime of that number gives the height of this rectangle, or here. And so that's going to look like this. Alright, the change in x is this length here, and the height is going to be this. And so the area of this rectangle equals the change in f equals the length of this green line here. So look at what happened here. If we zoom out a bit for a second, I know it's a bit sloppy. You just have to bear with me. But we have different representations of these changes here, right? We have an up change, we have a positive rectangle area. We have a down change, leads to a negative rectangle area, and another up change leads to another positive rectangle area. So what we did was, if I put this all together, I can sort of rewrite it. We could say that delta F1 is actually equal to f of x1 star delta x1, and delta F2 was equal to little f. Remember, the little f is the derivative of big F, x2 star delta x2, and so on and so on and so on. So what we can really do is we could write these in sigma notation. If we use a whole bunch of them, right? I mean, we only use 3, but it should be clear that I could repeat this process with however many. See, I only divided it into 3 separate groups, right? 1, 2, 3. But I could have done this a million times, and the result would have been exactly the same. In the end, what would have happened? We would have had a bunch of. We would have had more of these ups and downs, and that would have corresponded to a bunch of these rectangular boxes here, which if they get really, really small, you would see that they would start to conform to the shape of the curve. And what we would eventually get would be this if we did this over and over and over again with a lot of these boxes instead of just 3. Right? You would get enough boxes in here that it would totally fill in this entire space. And that would mean, if we could do that forever, that would give you the area, the net signed area between the little f function and the x-axis. So you can see this thing kind of coming together here. Let me just rewrite this. No. We started back up here. We said that the total change in f was the sum of, zoom in again, the total change in f was the sum of the individual changes in f. But via the mean value theorem and all the geometry that I just went through, this is also equal to the sum of the derivative, which is little f of xk star delta xk from k is 1 to n. So it's like a different way of writing it. Now if we have this all out on one line here, we can understand this. Total change in f, right? Some of the individual changes can be cashed in for an expression involving the derivative. Now wouldn't it be convenient if we were if we were interested in the actual area underneath the f prime curve? Wouldn't that be nice? See how it's coming together here. If we were interested in figuring this out, what we would do is we would do what I just did, only we would go backwards. You see how I started from this function, and the emphasis started out here, and I said, oh, by the way, the changes in this function can be represented by these rectangles here. Well, when we're going to find areas, the focus starts here. And this function, the derivative, all right, the big f prime, the little f, this is the function that we really want. I'm sorry, this would be the function whose area we would actually be interested in, right? So if we had some function that we wanted, under which we wanted to find the net signed area, what we would do with that function would be we would set up a limit that looked like this. And if we kind of go backwards, this gives us an alternative way of figuring out how to actually do it, where the relationship is the derivative of big F equals little f. Remember, these are the things that we would make if we were going to find if we were trying to calculate an area directly. We would fill all the space like so. Right, this is where we would start. We would start with some little f whose area we wanted to find, and we would say, okay, in theory, we would fill it up with all these rectangles, do it over and over and over again, and then eventually fill out the entire area. Well, this gives us a way, kind of like a side trap door, a way to calculate that, because each one of these rectangles, the areas of each one of these rectangles can be written as a change in the antiderivative of this function. And that's what this is all about, right? Instead of going this way, going from here to here, we could say that, oh, the areas of these rectangles can be represented differently. They can be written as changes in the antiderivative of the function that you're trying to find the area underneath. Oh, and that's what this statement is saying. And I hope you understand that. For each one of these like individual terms, there's a corresponding change in the antiderivative. So what we would do is, for all three of these, we would take the limit as delta x max approaches 0, meaning that we would drive this thing to 0, exhausting all the area underneath here, right? Filling this thing with rectangles, and at the same time getting an infinite number of these changes in f's, right? All these ups and all these ups and downs. Each rectangle here has a representation of up here, and so throughout all that, what you would get is the limit as delta x max approaches 0. Well, the limit as delta x max approaches 0 of this is just going to be what it is, right? Because we said earlier that no matter how we chop up our region, the end result is just going to be big F of B minus big F of A. It's going clearly to give us the change in the antiderivative no matter what, no matter how we chop it up. We could just kind of bypass this here, and when we take the limit as delta x max approaches 0 of this, what we get is the notation for the definite integral, a to b of f of x dx. So what we wind up with is we get this in the limiting sense equals this. So let me just write that down. After taking the limit, we arrive at the conclusion that big F of b minus big F of a, the change in the antiderivative, the total change, equals what you would get f of x dx from a to b, equals what you would get if you could add up all these rectangles forever and ever and ever. So one more time. So this is really the statement. This is the restatement of the link between antiderivatives and area. All right. Let me just go back one more time. What this is saying is that when you have some function and you want to find the area, the way that we do this is we make a bunch of rectangles here, and theoretically we would add up the areas of all these rectangles, and as we used infinitely many of them, and we would exhaust all the area underneath the curve, and that would be that. First of all, it'd be represented by this thing here. It would stand for the net signed area, but each of these areas, the areas of each of these rectangles, can be rewritten as a change in the antiderivative of this function from here to here, from the endpoints. So what happens is when you're adding up, like say this area here equals the change in the antiderivative from this point to this point, and then the area of this rectangle here gives us the change from this point to this point, thus giving me the total change from here to here, right? We sort of cut this middle guy out, and each one that we do, what you find is they kind of cancel each other out, all the up and down changes, so that all that's really left is excuse me, the ones on the ends, which is big F of B minus big F of A. And that is yet another way of looking at the fundamental theorem of calculus, how to find areas under curves using antiderivatives. Once again, please leave a comment. Let me know if this could be cleaned up or if it was unclear. Thank you very much.